Subscribe to the channel so you don't miss out on any of these videos. Space is an endless frontier filled with captivating mysteries, yet not everything in the cosmos is something we can see, touch, or even directly measure. Beyond the stars, planets, and black holes that we're familiar with lies a category of purely theoretical entities, the so-called hypothetical cosmic objects. These are forms and phenomena that scientists believe could exist but have yet to observe directly. Imagine objects so strange that they challenge the very nature of physics as we understand it, existing at the boundaries of reality, tethered to theories that delve deep into quantum mechanics, high-energy astrophysics, and relativity. Imagine for a moment an object from the earliest moments after the Big Bang, a relic from the universe's infancy, a primordial black hole, so ancient and enigmatic that it could hold clues to the birth of galaxies. Or think about quark stars, which pack the mass of a giant star into an object just a few miles across, dense beyond belief, consisting of the raw building blocks of protons and neutrons. And then there are cosmic strings, hypothetical one-dimensional defects in space-time, stretching across the universe, remnants from the earliest epochs of cosmic evolution. These are not objects you could see with the naked eye, nor can our current technology capture them in any traditional sense. But they might be out there, hidden in the cosmic tapestry, lurking at the limits of what we know and opening up new realms of possibility for what we don't. This journey through hypothetical cosmic objects challenges our understanding of the universe, requiring us to consider strange phenomena and push the limits of current scientific theories. Each of these theoretical objects holds its own mysteries, backed by speculative physics and supported by intricate mathematical frameworks. Yet they beckon with the promise of answers to some of the most profound questions we have about the cosmos. If these objects exist, they could fundamentally reshape our grasp of everything from how matter behaves under extreme conditions to how the universe was born, and what it may ultimately become. Let's begin with primordial black holes. When we hear black hole, we might think of massive, star-eating monsters scattered across galaxies. But primordial black holes are an entirely different kind of creature. Hypothetically, they formed not from the death of a star but from the immense fluctuations in density that occurred immediately after the Big Bang. These fluctuations, caused by tiny variations in the density of the early universe, may have created pockets where matter compressed to such extremes that gravity won out, birthing minuscule black holes right as the universe was just seconds old. These primordial black holes could range in size from tiny, subatomic scales to massive objects thousands of times the size of the Sun. Yet, despite their potentially vast number, we haven't observed them, at least not yet. The idea of primordial black holes is compelling not just because of their origins but because of what they could tell us about the early universe. They might even make up a significant portion of dark matter, the mysterious substance that we know comprises most of the matter in the universe but that we cannot see or directly detect. Primordial black holes could explain some of the gravitational anomalies attributed to dark matter, providing a visible source for what otherwise appears as invisible mass. Some theories even suggest that collisions between primordial black holes could produce detectable gravitational waves, and scientists have begun scanning these waves for signals that might confirm their existence. Moving on from primordial black holes, we encounter another hypothetical marvel of the universe, quark stars. To understand quark stars, we first need to consider what happens when a massive star dies. Typically, after a supernova, a massive star's core collapses, forming either a neutron star or a black hole. Neutron stars are incredibly dense, packing more than the mass of the Sun into a sphere only a few miles wide. However, some theorists suggest that under even more extreme pressures, the neutrons in a neutron star might break down into their constituent quarks, forming an object known as a quark star. This would make a quark star even denser than a neutron star, existing at the threshold where matter itself is broken down into the most fundamental particles. The physics behind quark stars is highly speculative, relying on concepts from quantum chromodynamics, QCD, the theory that explains how quarks interact. If quark stars do exist, they might represent a unique phase of matter, one that could only be created under unimaginable pressures. Studying quark stars could help scientists understand how matter behaves at the limits of density, potentially offering insights into the earliest moments of the universe, when similar conditions might have existed. Then we encounter the fascinating possibility of cosmic strings. Imagine a thread, impossibly thin but stretching across the universe, bending space and time along its path. These are cosmic strings, hypothetical one-dimensional defects in the fabric of the cosmos, thought to be relics from the very first moments after the Big Bang. They are believed to have formed during a period of symmetry breaking, a phase transition in the early universe when fundamental forces separated into their distinct forms. Similar to cracks that form in ice as water freezes, cosmic strings are theorized to be the cracks in space-time itself, tiny in width but potentially stretching across galaxies. If cosmic strings exist, they would create gravitational effects unlike anything else in the universe. Moving past a cosmic string would theoretically produce a phenomenon called a gravitational lens, where the string's gravity bends light around it. But unlike ordinary gravitational lenses produced by objects like stars or galaxies, cosmic strings would create unique, double-image lenses, splitting light from objects behind them into duplicate images. Detecting such a gravitational lensing effect would be strong evidence for the existence of cosmic strings. But beyond gravitational effects, cosmic strings might also create powerful bursts of gravitational waves, ripples in spacetime that could be detected by highly sensitive equipment on Earth. In many ways, these hypothetical objects push the boundaries of what's conceivable within the laws of physics. They force us to ask if there are forms of matter and energy that defy our current models, if there are remnants of the universe's birth scattered across space that could change everything we know about the cosmos. Each of these objects brings us closer to answers while simultaneously opening up even more questions. For every primordial black hole, quark star, or cosmic string hypothesized, there's a hint of something profoundly alien lurking out in the cosmos, waiting for us to develop the tools, technologies, or theories necessary to uncover them. But the existence of these objects also raises philosophical questions about the nature of discovery and the limits of human knowledge. Are we capable of truly understanding these exotic phenomena, or will they forever remain on the edge of our understanding? Each new theory about these objects relies on advanced mathematics and experimental science that are themselves pushing the boundaries of what we can currently measure or observe. And as we develop better instruments, from gravitational wave detectors to high-energy particle colliders, we may get closer to proving, or disproving, the existence of these bizarre entities. Primordial black holes, quark stars, and cosmic strings might seem like something out of science fiction, but they're grounded in real scientific speculation and mathematical models. These models push us to expand our understanding of the cosmos, even as we're faced with the daunting reality that some of these objects may never be observable with current, or even future technology. This tension between theoretical possibility and observational reality is one of the fascinating aspects of hypothetical cosmic objects. It reminds us that much of our universe is still uncharted territory, both physically and conceptually. One of the most compelling reasons to study hypothetical cosmic objects like primordial black holes is their potential role in dark matter. Dark matter remains one of the biggest mysteries in modern astrophysics. It neither emits nor absorbs light, meaning it can't be observed through telescopes, but its gravitational effects on visible matter, such as stars and galaxies, reveal its presence. Scientists estimate that dark matter makes up about 27% of the universe, yet its nature eludes us. Some researchers believe primordial black holes could account for at least a portion of dark matter. If so, locating and studying these ancient black holes could unlock clues to dark matter's elusive nature and provide a deeper understanding of the universe's composition. One interesting approach to identifying primordial black holes is through gravitational microlensing. When a primordial black hole passes in front of a distant star, its gravity bends the light around it, creating a brightening effect on the star that telescopes can detect. Microlensing events are rare and transient, but by carefully observing specific regions of the sky, astronomers hope to spot these occurrences, potentially confirming the presence of primordial black holes. Additionally, scientists are exploring ways to detect the high-energy collisions that primordial black holes might cause. The energy released in these collisions could be a source of cosmic rays or other energetic particles, giving us indirect clues to their existence. The notion of quark stars similarly intrigues researchers because they exist in a transitional state between what we know and what we can only speculate about. Neutron stars, already incredibly dense, are thought to collapse into an even more compressed form of matter under certain extreme conditions. This might result in a quark-gluon plasma, a state where protons and neutrons dissolve into their quark components. This process creates a theoretical quark star, where quarks, along with gluons, the particles that glue quarks together, are no longer confined within protons and neutrons but exist in a free-flowing sea of quarks. If quark stars do exist, they could appear slightly smaller and denser than neutron stars. They would produce distinct emissions and have unique thermal properties compared to neutron stars. Observing a quark star would give scientists an unprecedented look into matter under conditions far more extreme than anything achievable in a laboratory. Even if we can't directly observe the interiors of these objects, their unique signatures could eventually reveal their presence, helping scientists piece together the puzzle of high-density matter and offering clues to the conditions that may have existed in the universe's earliest moments. Cosmic strings take this mystery to an entirely new level, introducing concepts that bridge astrophysics and high-energy particle physics. These theoretical objects are thought to be remnants from the universe's inflationary epoch, a period of rapid expansion following the Big Bang. During this phase, the universe underwent symmetry-breaking events, causing forces that were once unified to separate. Cosmic strings are hypothesized to be defects that formed during these transitions, much like the cracks that appear in ice as water freezes. They could stretch across vast distances, even across galaxies, yet be incredibly thin, potentially no wider than a single atomic nucleus. If cosmic strings exist, they would exert immense gravitational influence, capable of bending light and producing powerful gravitational waves. Their discovery would revolutionize our understanding of space-time and could provide evidence for the theories of cosmic inflation and symmetry breaking, which are central to our understanding of the early universe. Gravitational wave observatories, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and its counterparts, are now sensitive enough to potentially detect gravitational waves from cosmic strings, though no definitive detections have been made yet. If detected, the unique wave pattern produced by a cosmic string event would stand out from other sources, such as merging black holes or neutron stars, giving scientists a new tool to investigate the universe's infancy. These hypothetical objects challenge the limits of science because they require us to go beyond observable phenomena and rely on models that we can't easily test. Yet, they are anchored in well-established theories. Primordial black holes, for instance, draw from principles of general relativity and cosmology, while quark stars are deeply rooted in quantum chromodynamics. Cosmic strings, meanwhile, originate from field theories that attempt to unify fundamental forces in the universe. Each object lies at the intersection of different branches of physics, bridging gaps in our understanding and offering new avenues for research. The quest to study hypothetical cosmic objects also reflects the evolution of scientific methodology. Historically, science has relied on observation and experimentation, but in the case of these objects, theorists have to create sophisticated models that may only be verifiable indirectly. This trend showcases how the scientific process adapts to explore ideas at the frontier of knowledge. New tools and technologies, like gravitational wave detectors, advanced particle accelerators, and more powerful telescopes, give us a fighting chance to detect these enigmatic entities, even if only by the smallest traces they leave in the cosmos. It's possible, however, that some of these objects may remain permanently beyond our reach. The idea of entities that are theoretically conceivable but observationally inaccessible touches on the philosophical notion of the limits of human knowledge. If quark stars, for instance, exist only under conditions that we can neither replicate nor observe directly, do they truly exist in a meaningful way? And if cosmic strings are spread so sparsely or emit gravitational waves so faint that we could never detect them, how do we reconcile that with our understanding of reality? These questions are as much about the nature of science as they are about the universe itself. The study of hypothetical cosmic objects is more than an exercise in theoretical physics. It's a journey into the unknown, an attempt to bridge the gap between what we know and what we believe could be true. As we continue to explore these mysteries, we also push the boundaries of human imagination, creating new possibilities for what the cosmos might hold. In a universe filled with tangible wonders, planets, stars, galaxies, and black holes, there remains room for the unseen, the untested, and the unimaginable. The potential discovery of any one of these objects would reshape astrophysics, particle physics, and cosmology, altering our view of the universe and perhaps even our place within it. Whether or not we ever find a primordial black hole, quark star, or cosmic string, the pursuit itself drives scientific progress. It prompts us to develop new technologies, refine our theories, and rethink what we consider possible. And so, the mystery persists, the search continues, and the allure of the unknown beckons us ever onward. As we gaze into the depths of space, we are reminded that the universe is a place of boundless wonder, where the boundaries of reality remain elusive and the answers we seek may lie just beyond the horizon of what we can see, waiting for us to reach further, to imagine, to question, and perhaps, to someday discover. The notion of hypothetical cosmic objects draws us into one of the most profound questions humanity has ever grappled with. Are we even capable of truly understanding the full scope of the cosmos? For every discovery, we seem to unearth countless more questions, and the tantalizing ideas of primordial black holes, quark stars, and cosmic strings serve as stark reminders of our limitations. And yet, paradoxically, it is these limitations that fuel our relentless curiosity. The more we discover, the more we realize how much remains hidden from view, as though the universe itself is nudging us toward deeper inquiry. Let's dig deeper into primordial black holes, for instance, and the potential for them to reveal the hidden layers of our universe's past. Unlike conventional black holes that form from the gravitational collapse of massive stars, primordial black holes are believed to have originated from density fluctuations in the very early universe. According to the theory, in the first fractions of a second after the Big Bang, there may have been regions where density was extraordinarily high. In these pockets, the gravitational forces could have become strong enough to overcome expansion, collapsing into black holes on a microscopic scale. These objects, born from the raw material of the Big Bang itself, could still exist, roaming undetected through space. Primordial black holes could range in size from incredibly tiny, subatomic particles, all the way up to masses of tens or even hundreds of times that of our Sun. Theoretically, smaller ones would have evaporated over time due to a process called Hawking radiation, but those of intermediate size might still persist. If primordial black holes indeed constitute part of the universe's dark matter, this would have immense implications, not just for astrophysics, but for particle physics and cosmology as well. Finding even a single primordial black hole would provide direct evidence of a period in the universe's history that current theories only hint at, a time when quantum fluctuations could have seeded structures that shape the universe we see today. In the same cosmic symphony, quark stars represent an entirely different frontier. These hypothetical stars, composed of strange quark matter, may emerge when neutron stars undergo further collapse but stop short of becoming black holes. The quarks inside these stars might be strange quarks, a more exotic version of the quarks that make up everyday particles like protons and neutrons. If strange quark matter exists and remains stable, it could signal an entirely new phase of matter, unlike anything we observe on Earth. This form of matter might exist in what scientists call a strange star, or a quark star, whose unique density and composition would make it an object of exceptional interest. Studying quark stars would not only expand our knowledge of high-density matter but would also deepen our understanding of the strong nuclear force, the force responsible for binding quarks within protons and neutrons. This force, one of the four fundamental forces of nature, is notoriously difficult to study because it only operates over extremely short distances. In the heart of a quark star, where quarks are no longer bound within individual protons or neutrons but roam freely, the strong force could behave in ways that current models struggle to predict. Observing or even just verifying the existence of a quark star would therefore be a monumental leap forward in both astrophysics and particle physics. And then there are cosmic strings, hypothetical relics from the earliest epochs of the universe, thought to have been formed as space-time cooled and stretched in the wake of the Big Bang. Unlike other hypothetical cosmic objects, cosmic strings are considered to be one-dimensional, infinitely thin but possibly infinitely long structures that weave through space like cracks on the surface of a frozen lake. These objects, if they exist, are thought to carry an immense amount of mass and tension, capable of distorting space-time in extraordinary ways. Imagine a thread, thinner than an atom yet capable of warping space like the gravity of a massive planet. This is the mystery of cosmic strings, an idea that merges high-energy physics with cosmology. If cosmic strings exist, they could potentially create gravitational waves strong enough to be detected by gravitational wave observatories like LIGO. The discovery of such waves from cosmic strings would serve as direct evidence for events that occurred during the universe's inflationary phase, adding support to our theories of cosmic inflation and offering new insights into the fabric of space-time itself. In fact, the study of gravitational waves, in general, has opened up a new way of seeing the universe, allowing us to detect events and objects that might otherwise remain hidden. If cosmic strings exist, they could also form loops, which would oscillate and emit gravitational waves, providing a unique signature for researchers to look for. Another intriguing aspect of cosmic strings is their theoretical connection to monopoles. These are another type of hypothetical particle, predicted by certain grand unified theories, that possess a single magnetic pole, north or south, rather than the typical magnetic dipoles seen in everyday magnets. According to some theories, monopoles could form along cosmic strings, creating magnetic charges that could vastly change our understanding of electromagnetism. Such particles have yet to be observed, but if they do exist and if they interact with cosmic strings, they could revolutionize our understanding of the universe's fundamental forces. This journey into the realm of hypothetical cosmic objects challenges us to reconsider our assumptions about the universe. The very idea of unseen and possibly undetectable objects stretches the boundaries of scientific inquiry. Historically, science has been a discipline of observation, a practice of constructing knowledge based on what we can see, measure, and test. Yet, the study of hypothetical cosmic objects pushes us toward a form of knowledge that is more speculative, relying on mathematics, indirect evidence, and models rather than direct observation. But that doesn't mean the pursuit lacks rigor. Each hypothesis about primordial black holes, quark stars, or cosmic strings is founded on established physical principles. They draw from what we know about gravity, quantum mechanics, and thermodynamics. These models are carefully crafted, grounded in the same scientific frameworks that have helped us uncover phenomena from the existence of black holes to the cosmic microwave background. However, unlike more established scientific phenomena, hypothetical cosmic objects force us to operate in a realm where even the tools of detection remain speculative. This is a space where ideas must wait patiently for technology to catch up. This field also exemplifies the collaborative nature of science, as each advancement in technology brings new potential for discovery. Whether it's gravitational wave observatories, particle accelerators, or even new space telescopes, each piece of equipment opens a window into previously inaccessible realms. Gravitational wave observatories like LIGO and Virgo, for example, have already proven their worth by detecting mergers between black holes and neutron stars. As these observatories become more sensitive, the possibility of detecting hypothetical objects such as cosmic strings becomes increasingly realistic. It's a reminder that, in the world of science, patience is as crucial as innovation. Looking forward, the continued pursuit of hypothetical cosmic objects will likely bring about technological advances that benefit other areas of science as well. For instance, the techniques developed to search for quark stars might offer insights into the behavior of matter at the atomic level, with potential applications in nuclear physics and even practical technologies. Similarly, the tools used to study cosmic strings and primordial black holes might eventually be adapted to investigate other astrophysical phenomena, from dark matter to exoplanets. At the same time, the search for these objects compels us to confront the limits of our own understanding. It's a humbling experience, to be sure, but also a profoundly inspiring one. It reminds us that the universe is not here simply to be understood, that there are mysteries woven into its fabric that might forever remain beyond our reach. And perhaps that is the ultimate mystery of these hypothetical cosmic objects, that they could represent a realm of existence so far removed from our own experience, that understanding them fully may never be possible. And yet, even as these mysteries taunt us with their elusiveness, they drive us forward. The quest to uncover the unknown remains one of humanity's most defining traits, pushing us to explore, to question, and to imagine. The stories of primordial black holes, quark stars, and cosmic strings might remain speculative for now, but they are no less captivating. In exploring these mysteries, we expand not only our understanding of the universe but also our capacity for wonder, leaving us with the profound realization that science is as much about asking questions as it is about finding answers. The pursuit of understanding hypothetical cosmic objects embodies humanity's collective yearning to explore, even when the answers seem eternally out of reach. We've built a civilization that values knowledge, a society that thrives on the quest for truth, where each discovery, even of something unseen or intangible, is celebrated as a step forward. Each theory, whether it concerns primordial black holes, quark stars, or cosmic strings, feeds a centuries-old narrative in which we refuse to accept the surface of reality as the final frontier. The unknown tantalizes and beckons us to pursue it, to ponder what lies just beyond our current understanding. Primordial black holes, for instance, continue to present a dual nature, balancing between fact and speculation. On one hand, they serve as mathematical solutions that offer intriguing explanations for certain cosmic puzzles. On the other, they remain as unseen, challenging scientists to bridge the gap between numbers on paper and realities in the observable universe. The implications of discovering even one primordial black hole would ripple across various fields. Imagine, for example, what it would mean for our understanding of dark matter. Scientists have long posited that dark matter, which makes up a significant portion of the universe's mass, might not be a new kind of particle at all, but rather a combination of exotic objects like primordial black holes. If true, this would redefine our understanding of the cosmos, grounding the mysterious, dark, part of the universe in physical objects, rather than in elusive subatomic particles. Then there's the mystery of quark stars, a concept so strange that it defies what we know about the very fabric of matter. Most people are familiar with atoms as the building blocks of matter, with protons, neutrons, and electrons forming their core. But in extreme conditions, as we might find in the heart of a neutron star, the distinction between particles could begin to blur. Protons and neutrons could dissolve into a soup of quarks, the fundamental building blocks of matter. This quark matter would exist in an even more condensed state than that of typical neutron stars, essentially forming an object so dense that it challenges our ability to visualize it. If quark stars do exist, they would represent a completely new phase of matter, something we've never encountered in our terrestrial experiments. Observing one would provide insights into the strong nuclear force, which binds quarks together, a force so potent that it resists direct study. Only under the most extreme conditions, like those within quark stars, could we truly observe its effects in isolation. This brings us to cosmic strings, theoretical objects that challenge the conventional understanding of dimensions and space. If a cosmic string truly exists, it would be as close to a singularity as we might find outside a black hole. A one-dimensional thread, infinitely thin yet infinitely long, a cosmic string could stretch through space without end, causing distortions that ripple across the fabric of space-time itself. Imagine a line in space that isn't just a point but a continuous fracture, capable of bending light and altering the path of anything that crosses it. Cosmic strings aren't just hypothetical for the sake of curiosity. They hold real stakes for our understanding of cosmic inflation, the period in which the universe rapidly expanded after the Big Bang. According to some theories, cosmic strings are remnants of this primordial event, a scar, left on space-time as the universe expanded. By studying cosmic strings, we might gain a glimpse into conditions that existed only fractions of a second after the Big Bang, offering a glimpse of a time beyond the reach of even the most powerful telescopes. Another profound layer of intrigue surrounding these hypothetical objects lies in the grand unification theories that physicists pursue. These theories seek to unify the fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single framework, describing the universe's fundamental interactions in one coherent model. In this pursuit, cosmic strings and quark stars could serve as a bridge between our current understanding and the mysteries of quantum gravity, the elusive theory that combines quantum mechanics with general relativity. Detecting a cosmic string, for example, might provide a real-world basis for these theories, allowing us to test ideas that otherwise exist only on paper. It's as though the universe has left us clues, a trail of breadcrumbs leading us back to its origins, if only we have the tools and the patience to follow it. Even though we have yet to observe these cosmic objects directly, the indirect evidence keeps building. For instance, researchers studying fast radio bursts, intense and fleeting emissions of radio waves from distant galaxies, have speculated that these bursts could be caused by exotic objects, possibly even quark stars. Similarly, scientists analyzing data from gravitational wave observatories are on the lookout for glitches or irregularities that might hint at cosmic strings. These theories may seem far-fetched, but science is built on the shoulders of such bold ideas. Many of our most celebrated discoveries began as whispers, theories that were scoffed at or dismissed, only to be confirmed decades later. Another captivating aspect is the role that technology plays in our quest to confirm these objects. Each new advancement, whether in telescopes, particle detectors, or computer simulations, acts as a key, unlocking new levels of understanding. Take gravitational wave astronomy, a field so new that its possibilities are barely understood. Already, gravitational waves have provided insights into the lives and deaths of black holes and neutron stars. If primordial black holes or cosmic strings exist, it's likely that gravitational waves will be the first way we see them. Similarly, advances in high-energy particle physics, driven by facilities like the Large Hadron Collider, continue to push our understanding of quarks and fundamental particles. In this sense, every step forward in technology brings us closer to finding these cosmic phantoms. There's also something poetic in the idea that some of these objects might exist forever unseen. Primordial black holes, if they're small enough, might never emit detectable light, forever evading our gaze. Cosmic strings might weave through galaxies, distorting space itself, yet never come into direct contact with a region where we could observe their effects. It's as though the universe has hidden some of its greatest marvels behind a veil, challenging us to look deeper, to think harder, to stretch the very limits of human ingenuity and imagination. And it's this tension, the sense of nearly touching the unknown yet finding it just out of reach, that makes the search for hypothetical cosmic objects so exhilarating. These objects serve as reminders of both the vastness of the universe and the limitations of human knowledge. They embody the mysteries of creation, the lingering questions about how our universe came to be, and the unfathomable processes that shaped it. They challenge us to confront the mysteries of space with humility, reminding us that, for all our progress, we are still infants in the cosmic timeline. The pursuit of these mysteries is not just about finding answers. It's about embracing the unknown, learning to ask better questions, and marveling at the beauty of a universe that refuses to be fully known. Our journey to uncover the truth about primordial black holes, quark stars, and cosmic strings may be endless, but it's a pursuit that embodies the best of human curiosity. It's a journey that encourages us to look beyond the horizon, to seek out the impossible, and to dream of worlds that may forever remain beyond our reach. In a way, these objects represent not just the limits of the cosmos but the boundless nature of human imagination. And perhaps that is their greatest gift, to remind us that, in a universe filled with mysteries, the act of seeking may be as profound as the discoveries themselves. As we ponder these hypothetical cosmic objects, we realize that they are more than just speculative entities. They are pieces of a grander puzzle, offering insights into the deepest laws governing our reality. Their theoretical existence encourages us to push the boundaries of physics, challenging our understanding of space, time, and matter itself. In a sense, each one of these potential discoveries could shift the course of physics, prompting new lines of inquiry and encouraging us to question what we think we know about the cosmos. Take primordial black holes, for example. If they exist, they could be unlike any black hole we've observed, offering a different view of gravitational collapse. Whereas conventional black holes form from the remnants of massive stars, primordial black holes would have originated from density fluctuations in the very early universe. Just fractions of a second after the Big Bang, regions of space could have collapsed under their own gravity to form these tiny but massively dense objects. This makes primordial black holes not only a potential component of dark matter but also historical artifacts, remnants from the birth of the universe itself. Studying them would be like unlocking a time capsule, revealing conditions that existed at the beginning of time. Imagine what it would mean if we could detect even one primordial black hole. It would confirm the presence of an entirely new class of celestial objects, but even more profoundly, it would validate theories about the high-energy environment of the early universe. For decades, scientists have theorized about what happened in those early moments, but we've had little direct evidence. Observing a primordial black hole would be like getting a snapshot of that time, frozen and preserved in space. It would tell us about the forces at play immediately after the Big Bang and might help refine our models of inflation, the rapid expansion of the universe that occurred fractions of a second after its formation. The mystery deepens with objects like quark stars. These theoretical stars challenge our understanding of matter on a fundamental level. Traditional stars, from red dwarfs to neutron stars, are supported against gravitational collapse by various forces: the pressure from nuclear fusion in main-sequence stars or neutron degeneracy pressure in neutron stars. But a quark star would push beyond even neutron degeneracy. In such an object, it's theorized that neutrons could be broken down into their constituent quarks, forming a state of matter denser than anything we've encountered. This form of quark matter, sometimes called strange matter, might be completely stable, or might only exist under the extreme pressures found within such an object. If quark stars exist, they would redefine our understanding of stellar evolution and introduce a new phase of matter beyond anything we can currently recreate in labs. Quark stars may also provide insights into the strong nuclear force, the force that binds quarks together and is responsible for the stability of atomic nuclei. This force is incredibly strong but operates only over extremely short distances. By studying objects where quarks exist outside the confines of protons and neutrons, we might gain a better understanding of how the strong force operates in conditions far beyond those found on Earth. It's a tantalizing possibility, one that could reshape particle physics as we know it. The discovery of a quark star would be a landmark achievement, offering a glimpse into the behavior of matter at its most fundamental level and challenging the boundaries between particle physics and astrophysics. Then we have cosmic strings, a concept that delves into the fabric of space-time itself. These one-dimensional defects would be unlike any other objects, forming continuous lines through the universe rather than existing as points or three-dimensional structures. Cosmic strings could result from phase transitions in the early universe, similar to how defects form in crystals when they cool. If they exist, cosmic strings would have extraordinary gravitational effects, warping space-time around them and creating gravitational waves that could be detectable even over vast cosmic distances. Some theories even suggest that cosmic strings could have contributed to the formation of galaxies, providing seeds around which matter could accumulate. If cosmic strings do exist, they might help explain certain large-scale structures we see in the universe, acting as cosmic scaffolding in the formation of galaxies and galaxy clusters. In terms of detectability, cosmic strings are particularly intriguing because they could generate observable phenomena. For instance, if a cosmic string were to pass between Earth and a distant star, it could distort the star's light in a way that would be distinguishable from other gravitational effects. This gravitational lensing effect could provide indirect evidence of cosmic strings. Additionally, cosmic strings could create detectable gravitational waves, adding a new dimension to our study of gravitational wave astronomy. Observing a gravitational wave caused by a cosmic string would be like detecting a faint whisper from the early universe, a signal that something extraordinary is hidden within the fabric of space-time. These hypothetical objects also touch upon one of the greatest mysteries in modern physics, the unification of quantum mechanics and general relativity. Quark stars, primordial black holes, and cosmic strings each represent conditions where our current understanding of physics breaks down or at least requires significant adjustment. Quark stars challenge our understanding of matter at the subatomic level, while primordial black holes and cosmic strings involve gravitational phenomena that test the limits of general relativity. By studying these objects, we might inch closer to a theory of quantum gravity, the elusive framework that would unify the behavior of the very large and the very small, reconciling Einstein's theory of general relativity with quantum mechanics. This pursuit of a unified theory is one of the greatest quests in science, and hypothetical cosmic objects could provide the testing ground we need. They serve as potential laboratories where the extremes of nature, enormous gravitational fields, ultra-dense matter, and the fundamental forces, interact in ways that we cannot replicate on Earth. By probing these objects, scientists hope to gather clues that will help piece together a coherent picture of the universe, a theory of everything that describes all known forces in one mathematical framework. Our understanding of the cosmos has always been limited by the tools we have and the vantage points we occupy. Hypothetical objects like primordial black holes, quark stars, and cosmic strings encourage us to adopt a new perspective, to consider phenomena that exist beyond our immediate perception. They push us to build better telescopes, to design more sensitive detectors, and to develop more sophisticated mathematical models. In doing so, these objects are not just puzzles to be solved but catalysts for innovation and discovery. As we build ever more advanced technologies, the potential to confirm the existence of these objects increases. Imagine a future where we have telescopes capable of detecting faint gravitational waves from cosmic strings, or where particle colliders can create conditions that mimic the interiors of quark stars. These advancements would not only confirm long-held theories but also open doors to entirely new branches of science. We would be entering a realm of discovery where the line between theory and observation blurs, where the universe's deepest secrets become visible. The pursuit of hypothetical cosmic objects reminds us that science is not static. It evolves as our tools and theories improve. The existence of these objects may still be unproven, but their study has already enriched our understanding of the cosmos. They serve as placeholders in our models, each one a promise of new knowledge and a reminder of how much remains unknown. As we look to the future, it's clear that the mysteries surrounding these objects will continue to inspire generations of scientists, pushing the boundaries of human knowledge and expanding our view of the universe. In a sense, these hypothetical objects are more than just scientific curiosities. They are symbols of the unknown, representing the vastness and complexity of a universe that refuses to be easily understood. They challenge us to think beyond the observable, to imagine what lies beyond the limits of our perception, and to acknowledge that even in an age of advanced technology, there are still mysteries that elude us. The cosmos is vast and enigmatic, filled with phenomena that inspire awe and humility. And as long as mysteries like primordial black holes, quark stars, and cosmic strings exist, we will continue our quest to understand the universe, one theory, one observation, and one discovery at a time. The quest to understand these enigmatic cosmic objects not only propels scientific progress, but also profoundly influences our philosophical perspectives. Each hypothetical entity represents a step further into the depths of the unknown, a challenge to our perception of reality, and a reminder of the mysteries that remain hidden within the cosmos. One compelling example of how these cosmic objects challenge our perceptions lies with the potential discovery of primordial black holes. If primordial black holes exist, they are not simply new members of the cosmic landscape, but could redefine our understanding of dark matter. Dark matter is one of the universe's most enduring mysteries, an invisible substance that makes up approximately 85% of the universe's total mass, detectable only through its gravitational effects. Though it plays a crucial role in shaping galaxies and large-scale structures, scientists have struggled to identify what dark matter actually is. Primordial black holes offer an intriguing possibility. If enough of these ancient black holes exist, they could account for a significant portion, if not all, of dark matter. Imagine the implications of such a discovery. If primordial black holes indeed account for dark matter, it would solve a long-standing enigma, while also opening new doors to understanding how structures in the universe evolved. Galaxy formation, for example, might need to be reevaluated in light of these ancient black holes influencing the distribution of matter. This would have repercussions across multiple fields of astrophysics, prompting a rethinking of theories on galaxy clustering, supermassive black hole formation, and even the potential for life in certain regions of the cosmos. The mere existence of primordial black holes would be a radical paradigm shift, and the possibility that they are dark matter would tie together some of the most elusive phenomena in modern cosmology. Moving to quark stars, the implications are equally staggering but rooted in the microcosmic rather than the macroscopic. A quark star, if found, would offer a new class of stellar object unlike anything we've observed. Neutron stars, previously thought to be the densest stable form of matter, are already among the most exotic objects in the cosmos, with densities so immense that a single sugar cube-sized portion of a neutron star would weigh billions of tons. Quark stars would take this density a step further. Their discovery would redefine what we know about degeneracy pressure, which is the quantum mechanical force that resists further compression in dense objects like neutron stars. Quark stars would not only reveal the conditions under which neutrons break down but might also showcase strange matter. The idea of strange matter stems from the notion that quarks within a star could exist as free particles instead of being confined within protons and neutrons. This state is hypothesized to be extremely stable, potentially even more stable than ordinary matter. If strange matter were discovered, it would introduce a hypothetical scenario called strange matter contagion, wherein any regular matter coming into contact with strange matter could transform into strange matter itself. While speculative, this theory underscores the depth of our ignorance about the behavior of matter under extreme pressures and challenges our assumptions about the permanence of atomic structures. Quark stars would also be astrophysical laboratories for exploring the limits of the strong nuclear force. On Earth, the strong force is one of the least understood of the fundamental forces, despite being responsible for holding atomic nuclei together. Under the intense pressures inside quark stars, scientists could study quark-gluon plasma and test theories about quantum chromodynamics, QCD, the branch of physics that describes the behavior of quarks and gluons. Discovering quark stars would be akin to finding a natural particle accelerator, offering a unique setting for exploring the inner workings of matter. Another layer of mystery surrounds cosmic strings and their role in the structural framework of the universe. If these one-dimensional defects exist, they would act as massive conduits of gravitational influence, warping space-time around them in ways that could profoundly affect the distribution of galaxies and clusters. Unlike typical celestial objects, which are point-like or spherical, cosmic strings would stretch across vast distances, threading through space as elongated, thread-like structures. The existence of cosmic strings could support theories of a multiverse or lend credence to ideas about extra dimensions, adding yet another layer to our understanding of space. Cosmic strings, being remnants from the early universe, might also carry clues about the forces that shaped our cosmos during its infancy. During cosmic inflation, as space expanded at an exponential rate, phase transitions could have led to defects in the fabric of space-time itself, resulting in these cosmic strings. If we were to detect one, it would be like accessing a fossil record of the universe's formative moments. Observing a cosmic string or its effects would confirm certain predictions from grand unified theories, GUTS, which attempt to unify the electromagnetic, weak, and strong nuclear forces under one framework. As such, the discovery of cosmic strings would provide a critical bridge between cosmology and particle physics, giving us clues about how the forces of nature might have been combined in the earliest moments of existence. In addition to gravitational lensing, which could distort the light of stars and galaxies, cosmic strings might also produce cusps, regions along the string that move at near light speeds. These cusps would emit bursts of gravitational waves detectable by current or future observatories. If detected, these gravitational waves would serve as direct evidence of cosmic strings and provide a new form of data about the universe's large-scale structure. Imagine gravitational wave observatories like LIGO, or the upcoming LISA, tuned to capture these ripples from cosmic strings. Observing these waves would allow scientists to peer across cosmic history, viewing events that occurred billions of years ago and vastly different from anything in our local universe. The exploration of hypothetical cosmic objects not only broadens our understanding of physics, but also impacts other fields like philosophy and metaphysics. These objects confront us with questions about reality itself. Are we capable of understanding the cosmos, or are there inherent limits to human comprehension? Hypothetical objects challenge us to rethink not only what we know but also how we know. For instance, if a primordial black hole were to pass through our solar system undetected, would it fundamentally alter the planet's orbits without any visible trace? This possibility reminds us that some cosmic phenomena might influence our world without leaving direct evidence, hinting at an unseen reality woven into the very fabric of existence. In a practical sense, these theoretical explorations drive technological innovation as well. The pursuit of understanding primordial black holes, quark stars, and cosmic strings requires us to develop new tools and methodologies. Innovations in gravitational wave detection, radio astronomy, particle acceleration, and computer simulations all stem from the need to probe deeper into these mysteries. This continual advancement of technology, motivated by the desire to understand the unknown, has ripple effects across countless industries, leading to new applications in medicine, engineering, and communication technologies. As the search for these hypothetical cosmic objects continues, we find ourselves at the frontier of human knowledge. While we may not yet have direct evidence for primordial black holes, quark stars, or cosmic strings, the pursuit of these mysteries embodies the spirit of science itself, a relentless quest to understand the universe in all its complexity. Even if these objects remain elusive, their theoretical study offers valuable insights and constantly challenges our assumptions. Through this pursuit, we redefine the boundaries of possibility, continually pushing the limits of what we can observe and comprehend. And so, the mystery endures. The cosmos remains an uncharted expanse, filled with phenomena that defy our current understanding. These hypothetical objects serve as beacons, guiding us toward deeper questions and bolder theories. They remind us that, despite centuries of scientific progress, the universe still holds secrets that await discovery. Each unanswered question, each new hypothesis, is a testament to the vastness of the unknown, a reminder that we are only at the beginning of a journey that may never truly end. As long as we continue to explore, to question, and to imagine, the mysteries of space will inspire and challenge us, beckoning us ever forward into the boundless cosmos. As we continue this journey into the unexplored reaches of space, the allure of hypothetical cosmic objects grows ever more captivating. These theoretical entities remind us that while we have mapped the planets, observed stars billions of light years away, and deciphered the mechanisms behind black holes, the universe remains filled with hidden layers. Each of these cosmic mysteries, whether primordial black holes, quark stars, or cosmic strings, represents a piece of a vast puzzle, an insight into forces and phenomena that stretch the imagination and challenge the boundaries of known science. Consider the potential impacts if just one of these objects were confirmed. A verified detection of a primordial black hole, for instance, would fundamentally alter our understanding of the early universe. Primordial black holes are theorized to have formed in the chaotic aftermath of the Big Bang, possibly within the first few seconds. The universe was then a roiling sea of energy and particles, with temperatures and densities that dwarf anything seen today. Within this extreme environment, density fluctuations could have been sufficient to create regions where gravity was so intense that particles collapsed into black holes. Unlike the black holes formed from collapsing stars, primordial black holes would have a range of sizes, including some far smaller than any known today. If these black holes from the universe's infancy are out there, they may hold clues about conditions that existed before atoms and galaxies. Finding a primordial black hole would be akin to peering into the Big Bang itself, revealing insights about high-energy physics, dark matter, and even the elusive field of quantum gravity. It would bring us closer to understanding the transition from a hot, dense state to the cooler, structured universe we see today. Additionally, The presence of primordial black holes could help answer questions about how galaxies and clusters formed, as their gravitational influence could have acted as seeds around which matter accumulated. One area of active research is the possibility that some of these primordial black holes could be microscopic in size yet have significant mass. Such objects, predicted by quantum theories of gravity, would be unlike anything observable through conventional telescopes. Due to their minuscule event horizons, they would not emit detectable amounts of Hawking radiation, a hypothetical radiation that causes black holes to lose mass over time, making them nearly invisible to most forms of detection. The quest to confirm or rule out such primordial black holes has inspired a wide range of detection methods, from gravitational lensing experiments to the search for anomalies in cosmic microwave background radiation. Quark stars, on the other hand, push our understanding of matter to its ultimate limits. Traditional stellar evolution tells us that stars end their lives in a predictable sequence. Low-mass stars become white dwarfs, while high-mass stars either go supernova and leave behind neutron stars or collapse further into black holes. But what if some stars take an even stranger path, condensing into an even denser form of matter? This is where the quark star comes in, a type of star so dense that even neutrons break down into their constituent quarks. Imagine the core of a neutron star undergoing such intense compression that it transitions into a quark-gluon plasma, a substance thought to have existed only in the first microseconds of the universe. A quark star would be a relic of this primordial phase, a natural laboratory for studying the fundamental particles that constitute matter. Scientists speculate that quark stars would have unique observational signatures. For example, their surfaces might emit bursts of high-energy gamma rays or X-rays due to the incredible densities at play. They might also produce gravitational waves distinct from those of regular neutron stars when they collide with other stars or black holes. Observing these signals would provide a powerful way to distinguish quark stars from neutron stars, offering a unique window into one of the most extreme environments known to physics. If strange matter exists in these stars, it might be stable enough to exist outside the confines of a star. In theory, if a small amount of strange matter were ejected from a quark star, it could survive indefinitely, traveling across space. This strange matter would be vastly denser than any material on Earth, potentially creating regions of highly compact, stable material that might persist for millions or even billions of years. Some theories even suggest that strange matter could exist in asteroid-like objects, hidden within the Milky Way or other galaxies, quietly drifting through space and remaining undetected. The mystery deepens further when we consider cosmic strings, a concept born from the union of cosmology and particle physics. Cosmic strings, if they exist, are remnants of symmetry-breaking events in the early universe, where the laws of physics underwent fundamental changes. These strings would be infinitesimally thin, yet immensely massive, stretching for potentially billions of light-years across the universe. One particularly mind-bending prediction about cosmic strings is that they could produce gravitational waves detectable by observatories like LIGO or the upcoming LISA mission. Imagine the universe as a vast ocean, with these cosmic strings creating ripples in space-time itself as they vibrate. Unlike gravitational waves produced by colliding black holes or neutron stars, cosmic string waves would have distinct signatures, revealing insights about the forces that shape the cosmos. Cosmic strings might even offer a route to exploring extra dimensions. Some theories in string theory suggest that cosmic strings could act as bridges or conduits to other dimensions, or that their presence could influence the geometry of space in ways that we cannot yet fully comprehend. Observing cosmic strings might allow us to test these theories, potentially revealing signs of higher dimensions or new particles predicted by grand unified theories. The existence of these objects also carries profound philosophical implications. They challenge us to rethink our place in the cosmos and confront the possibility that we might never fully comprehend all that exists. The hypothetical objects described here are, in a sense, symbols of the unknown. They represent the frontier of human understanding, a reminder that even with centuries of scientific discovery, the universe still holds mysteries that defy explanation. Pursuing knowledge about primordial black holes, quark stars, and cosmic strings isn't just about finding answers, it's about asking deeper questions. Could there be forces at play in the universe that we can't yet detect? Are there realms of reality that our instruments and minds cannot access? And if so, how do we reconcile our desire for knowledge with the inherent limitations of human perception and technology? The study of these objects also bridges the divide between the macroscopic and microscopic realms. In searching for primordial black holes, we explore the vast reaches of space and time, connecting the origins of the universe to its large-scale structure. Meanwhile, quark stars and cosmic strings take us down to the most fundamental particles and forces, linking cosmology with particle physics. This holistic approach underscores the interconnectedness of all things in the universe, where the smallest particles can influence the grandest cosmic structures. In a way, these hypothetical objects embody the spirit of scientific exploration. They are placeholders for the unknown, milestones on the road to discovery, and reminders of the vastness of the cosmos. While we may never observe these objects directly, their theoretical study has already expanded our understanding of the universe and pushed the boundaries of science. As long as we continue to push these boundaries, the mysteries of space will remain an endless source of wonder and inspiration. Each new hypothesis, each theoretical model, brings us one step closer to comprehending the cosmos. And in that pursuit, we find not just answers, but also a profound sense of connection to the universe that surrounds us. In this continued pursuit of cosmic mysteries, the notion of hypothetical objects acts as a powerful motivator for pushing the limits of both technology and theoretical frameworks. Each potential discovery, whether it be primordial black holes, quark stars, or cosmic strings, encourages humanity to develop new detection methods, new models, and new ways of interpreting reality. These hypothetical entities are like shadows cast by the unknown. We can infer their presence, but they elude our grasp, compelling us to look deeper and question further. Take, for example, the ongoing quest to detect gravitational waves from hypothetical cosmic strings. Advanced gravitational wave observatories like LIGO and Virgo have already made historic breakthroughs by detecting waves from black hole and neutron star mergers. However, these instruments are also fine-tuned to potentially pick up signals from other exotic phenomena, including the faint, continuous ripples that cosmic strings might create as they oscillate or interact. If we were to detect such a signal, it would imply the existence of cosmic strings, offering a glimpse into a primordial era of the universe when physical forces were unified in ways we barely understand today. A successful detection would open an entirely new field of study, with cosmic strings potentially acting as natural laboratories for testing theories of quantum gravity. As strings vibrate, they would create disturbances in space-time that could reveal aspects of quantum mechanics in conjunction with general relativity, a phenomenon that current physics has yet to reconcile. In essence, these strings might be fossils, from a time when the universe was governed by a single, overarching force, before it fragmented into the four known forces we recognize now. Then there is the tantalizing mystery of primordial black holes and their possible connection to dark matter. Dark matter remains one of the most enigmatic components of the cosmos, thought to make up about 27% of the universe's mass energy content. While dark matter has been inferred through gravitational effects on galaxies and galaxy clusters, it has never been directly observed. Some scientists hypothesize that a portion of dark matter could actually be composed of primordial black holes, scattered throughout the universe and silently contributing to the gravitational landscape of galaxies. The implications of this theory are profound. If primordial black holes do make up a portion of dark matter, it would indicate that some of the universe's mass is hidden within these elusive, ultra-compact objects. Detecting such black holes would not only provide evidence for these ancient remnants but also offer a partial solution to the dark matter puzzle, hinting that dark matter might be a diverse mix of objects rather than a single type of particle. Observational efforts to detect microlensing events, where the gravitational field of a black hole magnifies light from distant stars, could one day confirm or refute this theory. Quark stars, too, provide an equally fascinating lens through which to examine the extremes of matter. If quark stars exist, they would embody a state of matter more compact than even neutron stars, which are themselves incredibly dense. Such an object would redefine our understanding of stellar depth and the properties of matter at ultra-high densities. A quark star could compress particles to a level where they form a quark soup, potentially reaching temperatures and pressures similar to those found immediately after the Big Bang. The potential discovery of a quark star would mean that the universe contains a form of matter that has not been seen since its earliest moments, providing a window into the conditions of the primordial cosmos. This insight would have significant implications for nuclear physics, potentially revealing unknown behaviors of subatomic particles under extreme conditions. Moreover, the unique radiation emissions and gravitational wave signatures of quark stars could eventually enable us to distinguish them from traditional neutron stars, adding another piece to the puzzle of stellar evolution. Beyond scientific implications, the search for these objects also drives philosophical inquiry, challenging humanity's understanding of existence and our place in the universe. Hypothetical objects like cosmic strings suggest that the universe may be more layered and complex than we can observe, with structures that hint at phenomena beyond three-dimensional space. The idea that there could be extra dimensions hidden within the universe stretches the boundaries of the imagination, suggesting that reality may be far more intricate than our everyday experiences would indicate. The scientific quest to uncover these hypothetical cosmic entities also highlights the importance of imagination and open-mindedness in the process of discovery. Scientific progress is often driven by ideas that, at first glance, seem outlandish or impossible. The notion of quark stars or primordial black holes might have been dismissed as mere fantasy in earlier eras. Yet, as our understanding of physics deepens, these possibilities transform into areas of legitimate scientific inquiry. And while these theoretical objects currently reside at the fringes of science, their pursuit has already had tangible impacts on the field. Research into these mysteries has led to advancements in astrophysical modeling, data analysis techniques, and even new forms of instrumentation. For instance, the study of gravitational waves has advanced in part because scientists have sought to test for exotic objects like cosmic strings. Similarly, advances in high-energy physics have been driven by the need to understand quark-gluon plasmas, a state of matter that could exist within quark stars. Each new detection or non-detection brings us closer to a more complete understanding of the cosmos. Every experiment, observation, and theory developed in the pursuit of these cosmic enigmas builds upon the body of human knowledge, often with unforeseen applications. The search for primordial black holes or cosmic strings, for instance, has helped scientists refine their models of early universe inflation, contributing indirectly to our understanding of everything from galaxy formation to the structure of the cosmic microwave background. In this sense, hypothetical cosmic objects act as gateways, leading scientists to develop tools, theories, and methods that benefit all of astrophysics. The work done in the quest to understand these objects often spills over into other areas, enriching our knowledge of more conventional aspects of the universe and deepening our understanding of phenomena that we once thought we had already explained. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.